So yes, my name is Jared Webb, as was mentioned, and I work with the Michigan Data Science team, and I want to present to you some work we did working with the city of Flint and Google.org to understand the Flint water crisis. This is very much a tremendous collaborative effort, and I want to make special mention of my co-authors and collaborators. I see two of them here, Daniel Zhang and Alex Shanaki. They've done a lot of work, and the rest of the data science team as well. I also want to thank the Michigan Institute for Data Science and our faculty advisors, Jacob Abernathy and Eric Schwartz. So let's get started. I want to briefly introduce what MDST is. We're an outreach organization. We're run strictly by students. We came together in the fall of 2015, we thinking that we would be a small group working on Kaggle-style competitions for the fun of it. We dramatically underestimated interest, and we had many, many dozens of people wanting to work with us, and we soon expanded into more diverse projects. In particular, we've been interested in social good projects and projects that can benefit the communities around Ann Arbor. In the fall of 2015, the city of Flint and Google.org approached us asking for help understanding the Flint water crisis. And in the following months, we received hundreds of volunteer hours were freely given by MDST students, and that culminated in the work that we are presenting today. So for those of you that are unfamiliar with the Flint water crisis, I want to go over a brief outline, historical outline, to provide some context. This is very much a human story, even though there are interesting technical questions. And I think it does us a lot of good to keep that in mind. So first, understand that Flint was once one of the most prosperous cities in the United States, especially for the working class. However, in the 1970s, or starting in the 1970s, economic stagnation led to some severe financial constraints on the city. This was compounded in the financial crisis in 2008, and in 2011, Flint declared bankruptcy and went into emergency management. What that means is the state of Michigan appointed a single person to take charge of the city administration and put the financial footing on more solid ground. So this is where the water crisis begins. The emergency manager, as a cost-saving measure, decided to switch the source of water for the city from the Detroit municipal system to the Flint River, which flowed through the city. So this switch was finalized in 2014, and at the time of the switch, many residents of Flint complained about foul-smelling water or off-color water. Even some of them complained about rashes, but these complaints were mostly dismissed or ignored as anecdotal and not seriously investigated by the city. There is one remaining General Motors plant in Flint, and they noticed that the water became too corrosive for their manufacturing processes and had to switch sources. But the state and the city did nothing. So then in the fall of 2015, pediatricians who were working with children in Flint began to notice elevated blood levels, which is very concerning because lead poisoning is very damaging on the development of children. So soon after this spike in blood lead levels in children was noticed, the problem was identified and isolated as coming from the new water system. And this created a lot of media attention. The Flint River water, as it was moving through the infrastructure, was more acidic than the previous water supply. It stripped away a protective coating inside the pipes and pulled lead out of aging lead pipes into the water supply, and that entered the drinking water. And by January 2016, the state of emergency was declared. President Obama visited the city. Many celebrities were donating bottled water. Both presidential candidates visited the city, and there was even a debate hosted in Flint, Michigan between the Democratic candidates. Since that time, Flint has faded from the headlines, but there are many problems that remain. Lead levels have abated somewhat in the drinking water, and it is now deemed safe to drink for most people so long as they use filters on the point of distribution. There's also current efforts underway to replace all lead service lines and pipes with modern materials, and we're expecting for that process to end, hopefully, by the end of 2019. That said, we still need to understand the crisis, both what happened and the long-term effects. And This crisis is multifaceted. It's got political dimensions, it has social justice and environmental justice dimensions. The infrastructure project by itself is a tremendous project, but we primarily view it as an information crisis. There are some fundamental questions that simply could not be answered when people began to notice that lead was leaching into the drinking water. For example, where are the lead pipes? This was something that was not known. Which homes are most at risk of being having poisonous water? And how many of these homes are at risk? So in the next few slides, I'm going to talk a little bit about what we do know. I'm going to talk about many data sources that we pulled together to better understand this crisis, and then we'll talk about some things we've done to understand. So the first data source I want to mention is with the residential testing data source. When the state of emergency was declared, the state of Michigan made lead testing freely available to residents of Flint. What that means is you could go to a distribution location, get a bottle, an empty bottle, and you would follow a procedure to fill that bottle with water and then turn it in to the state. They would return an analysis of that water and tell you what level of lead you had in your water in parts per billion. And luckily for us, all of these test results became publicly available online. One thing that's interesting to note and underscores the complications of this problem is a cursory glance at the data will show that there's no salient pattern, geographic pattern anyway, in which houses had poisonous lead tests and which ones did not. Next door neighbors might have one safe water and the other very dangerous water. Another thing is many homes submitted more than one test. And so even though we had more than 20,000 submissions to work with, that only represented about 11,000 homes in Flint. In parallel with this residential testing program, we also ran what's called, well, we didn't run, a Sentinel water testing program was run. And this was run by the state in parallel with the residential water testing program. And what they would do is they chose some homes in Flint to be sentinels. Ideally, they chose these homes to be representative of the whole city, and every week they would send officials to these homes to measure carefully the water in those homes, hopefully to get a more quality controlled understanding of the water crisis. So this data is publicly available but anonymized, but the state of Michigan very graciously shared this with us to help understand the crisis. Another data source that we have to work with is Parcel Data. So a parcel is a unit of taxable land in a city or county. And Flint kept track of various things relevant to taxation, such as the size of a home on a plot, what year it was built, or the zoning for that plot for that particular parcel. This data is not publicly available in the form that was delivered to us, but you can find similar data in many cities using like tax websites. I want to make brief mention of the service line data. It's a story unto itself, very interesting. So most cities, well, first I'll explain what a service line is. Water is distributed to a neighborhood through water mains, big pipes that run parallel or underneath city streets. To connect your house to a water main, you have what's called a service line going from your water meter to the main. There's two paths of the service line. Part of it is your responsibility as a homeowner. Maybe you didn't know that, but it's true. And the other half is the responsibility of the city. Now, it was hypothesized that these service lines had lead in them. But at the beginning of the crisis, Flint could produce no records whatsoever of the service line materials in these homes. Most cities have very careful records, but Flint had misplaced theirs, I guess. So eventually, quite luckily for everybody, someone came across a box full of 3x5 handwritten index cards in the basement of a city building. And lo and behold, these index cards had small maps of the city hand-drawn on them and written records of the service lines. This was painstakingly digitized by students and Dr. Marty Kaufman at the University of Michigan Flint Extension. It was a lot of work, but they did it and they shared it with us, and we're very grateful. Since the time of discovering these records, There have been service line replacements throughout the city, and we've been able to update and keep track of how accurate they were. They are better than random guessing, but only just barely. So even though we had them, they're not exactly accurate. Finally, all the previous data sets I described are data sets having to do with the properties, the infrastructure, but nothing really specifically about the people living in those properties. And so we pulled data from the American Community Survey, which is a demographic survey run by the United States Census Bureau that provides highly localized estimates of various demographics across the United States. So we pulled information about population, age, race, income, languages spoken, etc. Partly we were interested in this data because we thought it might help explain a little bit, but also it helps us understand which populations are going to be affected the most by looking at the predictive factors in our models that I'll be discussing in just a second. So this is a trove of data. We believe that this data is the largest collection of data to describe a municipal water system in existence, certainly that describes this water crisis. But now that we've spoken about the data, I want to talk about what we want to know. We really want to be able to produce estimates of how dangerous water is at the parcel level. We want to say, for each house, how dangerous is the water coming out of your tap? Besides that, we also want to know which homes are making submissions and getting tested and which aren't. Are there populations that are underserved? We'll be talking first about the lead prediction task. We have over here a map that we generated. We want to turn all this data that we put together into this prediction. Which homes are most at risk of having poisonous water in them? So we trained many models. We had the most luck with tree ensemble models, which I think is to be expected with a data set like this. And in particular, we got the best performance out of XGBoost, but it was comparable in performance with random forest and extremely random trees. Even so, our predictions are not super great. I think they're great, but after choosing hyperparameters and optimizing our models, we got a cross-validation score of about 0.72 with pretty much right on the nose across splits. This underscores the difficult nature of predicting things of this, predicting which homes have dangerous water in them. But I do want to make particular mention, if you pay attention to this rock curve down at the bottom left, we do have a very steep increase at first. The properties we're most certain about are we get very good predictions there. We're very accurate. Only after we decrease uncertainty do we start to see diminishing returns in our predictive power. So when it comes to a resource allocation problem, this is encouraging, that we could at least say these properties we are very certain have the most dangerous water, and you'll have success if you test that. Even so, we wanted to see if we could improve our scores by crowdsourcing a little bit. We ran a prediction challenge with our data with Kaggle in class, and we sought to see if we could improve our scores. So we took 17,000 of our water tests from 11,000 homes, and in total, 150 teams worked on this at the University of Michigan. We had more than 500 submissions. The winning submission was for anyone that's done Kaggle contests before, was an ensemble model. So it's what we would expect. But the ROC score was not much better than what we were finding on the slightly bigger data set. So we feel confident that this is what we can learn and what we can predict. Let me briefly talk about some of the impact this work has had. I mentioned that we were working with Google.org, and they generously supported work on producing a web app and an Android app to deliver this information to the residents of Flint. So what happened is we created an interactive map that you could zoom in on your house or your neighborhood, and you could click on each home and get an assessed risk for that home, whether high or low, and whether we recommend testing at that home. And then we also record the water test results. So if your home has already been tested, that shows up on the map and tells whether you had low or high lead levels. So let's move on to our other test, our other problem we were interested in studying. We wanted to understand submission behavior. And So we trained a weak classifier to try to predict whether a home would make a submission or not. This was an out-of-boost classifier that was regularized heavily. And we saw that the most predictive factors were land and home value, the year a home was built, and the state-assessed condition of the home. Forgot to mention this, but this is very similar to the predictive factors for our lead level predictions. So we thought that maybe this could represent some sampling bias. The residential water treatment program is voluntary after all, and there may be that only people that are maybe more well-connected, but are educated, are the ones making submissions, and maybe that is skewing our results. So in order to correct for the sample bias, we tried, especially when calculating statistics, we tried reweighting the data that we had. So for example, if we wanted to calculate the 90th percentile average amount of lead in a water test, we would reweight our sample data using a reweighting technique, which I'll mention in a second, in order to get a more accurate result. So there are very sophisticated ways to correct for this, and unfortunately space constraints on this paper limited our how much we invested in that, but we did observe that by using kind of a heuristic technique, by combining our predicted submission results with our statistical calculations, we reweighted each sample inversely to our predicted probability of submission. We thought that would be a good proxy for over-representation. And eventually we did make some comparisons with this heuristic and the more sophisticated techniques, and we saw that it worked pretty much just as well. So after we corrected the bias, here we have a graph representing 90th percentile lead levels. The unbiased, the uncorrected weights are the red bars, and the corrected weights are the orange bars. We see that the changes were not that drastic in most months. This is important because it gives some evidence that this voluntary residential treatment program was more representative of the city than the Sentinel program that was supposed to be more accurate and more highly controlled. On the left here we have, your left. We have a screenshot tweet from Governor Rick Snyder of Michigan. After a few months of the crisis, he was very anxious to show improving conditions in Flint, and showed that that over time, water safety was increasing. This graph is measuring safety. Our graph is measuring danger. And if you look at the same time span, you'll notice that the corrected weights show that danger was actually increasing over the same time span. And in fact, peaked that summer after the crisis had been well underway for a while. Governor Snyder quickly deleted that tweet, but we got a screenshot. So I'd like to sum up really quick. I'm running out of time. I've observed that these lead tests are highly scattered. That said, they can be weakly predicted. And the predictive factors of that test help the city of Flint understand what is driving the crisis, what is driving water to become poisonous. We've shown, or we have evidence anyway, that the residential testing program is sufficiently representative of the city to draw these conclusions. In addition, we have some continuing work that we're doing. We have moved on from predicting water to predicting where lead pipes actually are in the city. This we are able to do with much better accuracy than predicting the dangerous water. And we are working together with the city of Flint and their recovery project in that aspect. Thank you for your attention, and I want to once again thank our Google.org, the National Science Foundation supported some of this work, and the Michigan Institute for Data Science, and also the Michigan Data Science team, who have been done an excellent job working together to, without getting paid or anything, just because they wanted to help. I'm very grateful for them, and thank you for your time.
Thank our speaker.